In 1923, a young engineer named Clarence Hansel was working in an aviation lab, studying ways to improve the stability of aircraft. Back then, in the early 20th century, aviation was really risky. Pilots had to rely on fairly basic instruments. A misjudged or miscalculated maneuver could send their aircraft into a spin. But Hansel had an idea that if you could measure small changes in movement and orientation, you could create a device that would help to stabilize planes automatically. Using a simple mechanical system with small suspended masses, Hansel created one of the earliest versions of an accelerometer, a device capable of detecting acceleration and movement. And by the 1930s, the military and aerospace industry had begun incorporating these accelerometers into all their aircraft instrumentation to improve navigation and stability. But the real transformation came in the 1950s and 60s with the Apollo space program. During this time, NASA engineers refined accelerometers and gyroscopes to track spacecraft movement with increasing precision. The Apollo guidance computer, the digital brains behind the moon landing in 1969, relied on an inertial measurement unit, or IMU, a combination of accelerometers and gyroscopes, to help astronauts navigate the vastness of space. That changed with the advent of microelectrical mechanical systems, or MEMS, technology in the 1980s and 90s. Basically, engineers found ways to shrink accelerometers and gyroscopes to microscopic scales, making them cost-effective and widely usable. Suddenly, this technology was everywhere, in airbags to detect collisions, in gaming consoles like the Nintendo Wii to track motion, and eventually in smartphones, smartwatches, and other wearable fitness trackers to monitor movement and activity. Today, accelerometers and gyroscopes are embedded in everything from Fitbits to Apple Watches. They're the underlying sensing modalities that allow these devices to track steps, turns, detect falls, and even car crashes. But how do these tiny sensors actually work? That's what we'll be covering today. At its core, an accelerometer is a sensor that measures acceleration, the rate at which an object's velocity changes over time. In simple terms, it detects movement, whether it's a sudden jolt, a smooth shift in direction, or the pull of gravity itself. Modern wearables primarily use what are known as capacitive accelerometers that rely on that MEMS technology developed in the 1980s and 90s that I mentioned before. Basically, inside the accelerometer, a small movable mass is suspended by microscopic springs. When the device moves or accelerates, this mass shifts slightly, altering the capacitance between tiny electrodes and ultimately their ability to store an electrical charge. This change in capacitance is converted into an electrical signal, which the device interprets as movement. Now, there are actually a few different kinds of accelerometers, each with different mechanisms of action, but ultimately serving the same purpose: detecting movement. The type most commonly found in wearables is the capacitive accelerometer, which, as I mentioned, detects motion by measuring changes in capacitance. But there are a couple of other types worth knowing about. Piezoelectric accelerometers work a little differently. Instead of measuring capacitance, they use special materials, things like quartz or ceramic crystals, that generate an electrical charge when subjected to mechanical stress. So when you move, the tiny internal mass inside the accelerometer applies force to these crystals, and they produce a voltage that corresponds to the movement, to the acceleration. These sensors are really sensitive and are typically used in industrial settings, where detecting very fine movements is important. They're not typically used in a consumer wearable device because they struggle to detect static acceleration, the constant force acting on your body like gravity or friction, which is needed for applications like step counting or gesture detection. Then there are piezo-resistive accelerometers, which work by changing their electrical resistance when subjected to mechanical stress. These types of accelerometers are usually found in high-impact applications like crash detection systems in cars, where rapid, forceful movements need to be detected. Again, they're not ideal for wearables because they tend to consume more power and aren't as precise at measuring subtle, continuous movements. So for the kinds of devices we wear on our wrists or clip onto our clothes, capacitive accelerometers are the most common. They're tiny, they're power efficient, and they're sensitive enough to pick up everything from small hand gestures to the impact of a foot hitting the pavement when you're running. But here's the thing, accelerometers alone don't give us the full picture. They're great at detecting linear motion, meaning movement in straight lines, but they don't tell us anything about rotation. If you spin in place without actually moving forward or backward, your accelerometer won't pick up much. This is why wearables also rely on another key sensor, the gyroscope. A gyroscope measures angular velocity, or how fast something is rotating. Think about how your smartphone screen rotates when you turn your device. It's not the accelerometer doing that, it's the gyroscope detecting the change in orientation. In a smartwatch, the gyroscope works alongside the accelerometer to distinguish between different types of movement. So for example, when you swing your arm naturally while walking, the accelerometer detects the up and down motion, while the gyroscope senses the rotation of your wrist. And together, when the signals from these sensors are combined and processed, they allow your device to count steps or differentiate between different kinds of activities and recognize gestures like raising your wrist to check your time. But even with an accelerometer and a gyroscope, there's actually still room for error. That's because gyroscopes suffer from drift. You see, because gyroscopes measure angular velocity rather than absolute position, small errors in measurement accumulate over time, and this results in inaccuracies in motion tracking. So to counteract this, some devices also include another sensor known as a magnetometer, which measures the Earth's magnetic field and provides a reference point for orientation of the gyroscope, helping to reduce errors in motion tracking. Now, when you combine an accelerometer and a gyroscope, and sometimes a magnetometer, you get what's known as an inertial measurement unit, or an IMU. Together, these sensors in an IMU can provide 6 degrees of freedom or 9 degrees of freedom motion tracking, meaning they can track movement in 3 translational directions: the sagittal, frontal, and transverse planes of motion, and 3 rotational directions: roll, pitch, and yaw. Plus, if a magnetometer is included, they can determine absolute orientation relative to the Earth's magnetic field. The IMU is the sensor package at the heart of motion tracking in most wearables these days. That's the technology underpinning when your device tells you to stand up because you've been static too long. They're used to measure your activity levels. They can track a run even without GPS, or detect a fall. They're the core technology behind sleep tracking by measuring your movement when you sleep. And IMU data is often fused with data from other sensors like PPG or photoplethysmography, which is used to measure heart rate for even better accuracy. So with all of this in mind, it's important to note that motion tracking isn't just about collecting raw sensor data and reading it out like a speedometer. There's a lot of signal processing, filtering, and machine learning involved to make sense of the data from each of the sensors, the accelerometer, the gyro, and the magnetometer. That's why modern IMUs don't just collect raw sensor data. They integrate information using sensor fusion techniques. By blending data from multiple sensors, advanced algorithms like Kalman filters or machine learning models can be used to improve accuracy and eliminate noise. Without sensor fusion, motion tracking would be jittery and unreliable and inaccurate. It's the reason your fitness tracker can tell the difference between walking and running, and why your phone's augmented reality applications, let's say something like Pokemon Go, can provide smooth, immersive experiences. So with that in mind, let's take a step back and have a look at what accelerometers and IMUs more broadly are used to measure. The simplest and most well-known application of accelerometry in wearables is step counting. Early pedometers like the Manpo K, which I've talked about in other videos, mainly relied on mechanical levers that moved up and down with each step, but modern step counters use accelerometers to detect the characteristic vertical oscillations of walking. When you take a step, your body moves up and down in a predictable pattern, and this generates small spikes in acceleration. By setting a threshold for these spikes, an algorithm can determine when a step has occurred. Those early devices relied on mechanical levers that shifted with each step, but today, step counters use accelerometers to detect the characteristic vertical oscillations of walking. Every time you take a step, your body moves up and down in a predictable rhythm, generating patterns in acceleration. By analyzing these patterns, a wearable device determines when a step has occurred. But there's a problem with this basic example. Real-world movement is not as predictable as a controlled lab environment. People walk in different ways, some with long strides, some with short, and others with quick steps. Some move with their hands in their pockets, others push strollers or shopping carts. Wearables have to account for these variations, distinguishing genuine steps from similar movements caused by driving over a bumpy road or tapping a foot to the beat of music, for example. That's where sensor fusion techniques come in. Most modern wearables now incorporate gyroscope data to measure steps, and this enables them to differentiate between stepping and other rhythmic wrist movements like brushing your teeth or typing on a keyboard. So for example, the very first Fitbit, which was released in 2009, had a single triaxial accelerometer to measure physical activity, including step counts, sleep, and energy expenditure. Today, even the most basic Fitbits have a full suite of motion sensors, accelerometers, gyroscopes, magnetometers, and GPS, so they're way more accurate than the early versions. And sensor fusion techniques are the reason that, beyond simple step counting, modern wearables can classify entire activities, distinguishing between walking, running, cycling, swimming, and even more complex exercises like yoga or strength training, albeit with varying degrees of accuracy. You see, each activity carries a unique motion signature. Walking produces a steady rhythmic acceleration with relatively low impact, while running exhibits higher acceleration spikes and greater force. Cycling, by contrast, lacks vertical oscillation but follows a characteristic forward-backward cadence, and swimming generates smooth, cyclical acceleration patterns with minimal impact forces. Whatever the scenario, wearables employ software algorithms to segment motion data into short intervals and extract key movement characteristics, comparing them against known activity patterns. The challenge is that most consumer wearables are wrist-worn, and this means that they rely heavily on upper body motion, which doesn't always accurately reflect lower body or whole body activity. Some devices compensate by incorporating heart rate data, using an increase in heart rate to confirm that a user is exercising, even if their wrist remains relatively still. Others are now integrating deep learning models, allowing wearables to improve classification accuracy by adapting to individual movement patterns over time. The point is, sensor fusion techniques are key to improving accuracy, and they are still relatively nascent in terms of their development. Another use case for motion sensors in wearables is fall detection. Falls are a leading cause of injury among the elderly, and the ability to detect them quickly can be life-saving. Fall detection relies on a combination of accelerometer and gyroscope data, searching for specific patterns that indicate a sudden loss of balance following impact. A typical fall detection algorithm might look for 3 events: a rapid acceleration spike, an unexpected rotation, and a period of stillness, for example. If all 3 occur in sequence, the wearable may trigger an alert, prompting the user to confirm whether they need assistance. In the absence of a response, some smartwatches automatically notify emergency contacts, or even call emergency services. But fall detection presents its own set of challenges. Wearables have to differentiate between genuine falls and everyday sudden movements, like dropping the device on a table or performing a quick, forceful motion like jumping or lunging. False positives can be frustrating for users, leading to unnecessary emergency alerts. So, to reduce errors, fall detection algorithms now incorporate contextual awareness, analyzing the user's movement before and after the detected event. If the data suggests the person was engaged in physical activity immediately before the event and resumes movements shortly afterwards, the device is less likely to interpret the incident as a fall. Beyond physical activity and event detection, IMUs are becoming a core part of sports performance tracking. Yes, athletes and fitness enthusiasts rely on wearable motion sensors to count their steps and track their sleep, like the general population, but they can also analyze performance and technique in precise detail. For example, in running, sensor fusion applied to accelerometer and gyroscope data can be used to measure stride length, cadence, and ground contact time, providing insights into running efficiency and potentially even injury risk. In sports like weightlifting, IMUs can be used to track barbell velocity and range of motion, helping athletes to map their performance or monitor their recovery. Professional sports teams increasingly integrate IMU-based motion tracking into training, embedding tiny sensors in clothing or equipment to monitor player movement in real time. This level of biomechanical analysis allows coaches to assess player performance, refine training regimens, and even predict injury risks based on movement inefficiencies, although it has to be said that it's still early days as to the extent of the benefit this level of monitoring provides. One of the most exciting frontiers in wearable motion tracking is its potential role in health diagnostics. Researchers are now exploring how IMUs can be used to detect early signs of neurological disorders like Parkinson's disease. Since Parkinson's affects motor control, subtle changes in gait and movement patterns can serve as early warning signs long before the traditional symptoms appear. While a lot of this research is still in its early stages, longitudinal studies suggest that continuous motion monitoring through wearables could provide valuable insights into disease progression and allow for earlier intervention. It's important to note, though, that most Parkinson's research relies on motion sensors placed on the lower body, such as insoles or waist-mounted IMUs, rather than wrist-worn devices, which have limitations in capturing detailed gait characteristics. So, motion sensors are transforming the way we track physical activity and monitor health, but they're not a perfect solution. They're prone to errors. Without careful calibration and signal processing, they can produce misleading or inaccurate data, and then motion artifacts, sensor drift, calibration issues, and battery life can all separately or in combination undermine the quality of the data IMUs generate. One of the most common problems in motion tracking is motion artifacts, which occur when external factors introduce noise into sensor readings. Imagine you're riding in a car while wearing a smartwatch. The accelerometer inside the watch detects movement, but is that the motion due to your own body moving or simply the car accelerating? Similarly, if you are running on a treadmill but holding onto the rails, your smartwatch might detect fewer steps than you actually take because your wrist isn't moving as much as it normally would. These types of errors are particularly problematic for activity recognition algorithms, which rely on pattern analysis to classify movements. If the data is contaminated with noise from unintended motion, the algorithm might misclassify activities or overestimate energy expenditure, for example. To address this, manufacturers again use sensor fusion techniques, combining accelerometer data and gyroscopes, heart rate sensors, and machine learning models to filter out incorrect readings. More advanced wearables also apply context-aware algorithms, which consider external factors like GPS, altitude changes, and previous movement history to improve accuracy. Another issue is sensor drift, and this is something that mainly affects gyroscopes. You see, unlike accelerometers, which have a fixed reference, gravity, gyroscopes accumulate small errors over time, and this causes them to lose accuracy. A gyroscope might initially track your movements correctly, but after a few minutes, it may start reporting slight rotations even when you're perfectly still. This is a big challenge in applications requiring precise motion tracking, like during sports performance. Over time, even a tiny drift can lead to large discrepancies in orientation estimates. To correct for this, many IMUs also include magnetometers, which detect the Earth's magnetic field and provide a stable reference point. But magnetometers introduce their own problems. They can be thrown off by metal objects and electromagnetic interference, making them unreliable in certain environments. Another common issue is calibration drift, where sensors lose their accuracy due to temperature changes, aging, or mechanical stress. If a smartwatch isn't properly calibrated, it may underestimate or overestimate step counts, misclassify activities, or even fail to detect falls. To compensate for these issues, a lot of devices include self-calibrating algorithms which periodically recalibrate sensor baselines based on known motion patterns. Another issue stems from the fact that motion tracking is computationally expensive, and frequent sensor sampling drains battery life. High-end smartwatches like the Apple Watch and Garmin devices use continuous motion tracking, but this comes at the cost of shorter battery life. To extend battery performance, some wearables use low power modes, reducing the sampling rate of motion sensors when the movement is minimal. For example, if a smartwatch detects that you are sitting still, it may switch to a low power motion mode, sampling accelerometer data less frequently. When movement resumes, the device reactivates full tracking, but this trade-off can sometimes lead to missed motion events, especially for activities that involve subtle movements like stretching or yoga. More recently, some wearables have started to use adaptive sampling rather than just low power modes. For example, Apple Watches and Garmin devices adjust sampling frequency dynamically, only recording at high precision when motion is detected. And then you have the issue that not all wearables use the same motion tracking algorithms. A step counted on a Fitbit might not match the step count from an Apple Watch, and a workout session recorded on a Garmin may have a different calorie estimate than the same workout on a Samsung Galaxy Watch. This variability is caused by underlying differences in sensor placement, algorithm design, and data processing techniques. Essentially, each company uses its own proprietary signal processing methods, and this makes it difficult to compare data across devices. While there are some standardization efforts underway, there really is no universal benchmark for motion sensor accuracy in consumer wearables, or any other sensing modality for that matter. This makes it really difficult for researchers to leverage wearable data at a population scale to better understand public health, or even to validate wearable data against gold standard motion tracking techniques. Even with these challenges, motion sensing technology does continue to improve. One of the most significant trends in wearable motion sensing is the integration of artificial intelligence and deep learning. Current activity recognition models rely on predefined motion signatures, but AI-driven systems could learn directly from users, continuously refining their ability to classify movement. So for example, the motion sensors in a smartwatch could leverage signal processing techniques in AI to adapt your behaviors. They might start by using generalized movement patterns to detect when you run, but over time it would adapt to your specific stride length, your cadence and arm swing, and this would make its predictions more personalized and accurate. AI models could also detect subtle differences in your movement signature, and this could help them to sort of recognize complex activities like weightlifting, dance, or even medical rehabilitation exercises. In the long run, wearables will not only track movement, but will also interpret it in more meaningful ways, offering deeper insights into health, fitness, and even early disease detection. But with this growing capability comes an important question. How should we handle the vast amounts of personal motion data being collected? As wearables become more sophisticated, discussions around data ownership, privacy, and security will be vital. But that's a topic that deserves its own video.